Hi everyone. I'm gonna do my best to keep this video as short as possible, but bear with me because there's a lot of information that we need to get through. This is about connecting polar equations with parametric equations. Hopefully, you remember some stuff about polar equations, so that this will go a little bit faster for you. Obviously, skip through stuff that you don't need, and then move on to the stuff that might be the most important for you. All right, so we're going to start off by, remembering some of these shapes, how they graph, and also turning them into parametric equations. So we're really going to work on connecting polars with parametrics in this section. So up here, you can see that we talk about using these two equations, which are really what we focus on when we talk about polars. X equals r cosine theta and y equals r sine theta. But we're going to use those also to write parametric equations. So when I ask you to write a parametric equation from a polar equation, this is what you're going to use to convert that. Okay, so this first one, I'm just going to go through them. And if we were in class, I would have you try and remember them, but we're just going to go through these to get them done. So this first one is a circle. And when you graph a circle in polar form, this is a circle that has symmetry over the polar axis. It has a diameter of 4, 1, 2, 3, 4 here. So there's the length of the diameter, and the circle is going something like this. To turn this into parametric equations, what you do is you take this x equals r cosine and you rewrite it as x equals. Okay. And you see what r is there, and then you're going to multiply this r by that cosine. So r here is 4 cosine theta. My stylus isn't working very well. And then I multiply that by cosine. So this is the x parametric equation. And then the y is 4 cosine theta times sine theta. So pretty much anytime you're doing turning parametrics from polars, you're going to have the equation that's r, and then for the x parametric, you'll multiply by cosine, and for the y parametric, you'll multiply by sine. Okay, the next one is a cardioid. When the two values are the same, it creates a cardioid just in time for Valentine's Day. So there is the name of it. This is, since it's sine and it's negative, this cardioid, the majority of the heart is going to be below the x-axis. So the length of the cardioid is here. The two edges are over here, and it makes this kind of heart shape on the graph. Sorry for my poor shapes, but again, my stylus isn't working very well. My parametric equations would be 2 minus 2 sine theta times cosine of theta, and y equals 2 minus 2 sine theta times sine of theta. Now you're also asked, where's my mouse here, to talk about how long it takes for each graph, for each shape to graph. So what we're talking about is how long in terms of theta does it take for this thing to create this graph. Again, if we were in class, I would show you on Desmos, but for the sake of time, I'm just going to give you the answer to these. And if we have time in class on another day, we will do this. So these circles that are symmetric to the polar or pi over 2 axis, they actually graph from 0 to pi. And the cardioid graphs from 0 to 2 pi. Okay, so the next two shapes are both limacons, but one of them has a loop and one of them does not. So this one is a limacon with a loop, and you know that because the first value, the 1, is smaller than the second value. So sine, positive sign, it's going to be mostly up. To get the large loop, you're going to add them together. So 1, 2, 3, 4. To get the inner loop, you're going to subtract 1 from 3 to get 2. And then you're going to graph at those little edges there. I wish my graph were a little bit bigger for you to be able to get a better look at that. I'm going to remind you that Desmos does a great job of graphing these. So if you're not sure, you can't remember, stick it on Desmos. It'll really help you out. Your parametrics. Oops. So there are the parametrics and Lima-san's graph on the window 0 to 2 pi. And it'll be important for you to remember these when we get into finding area in between the regions in polar curves. So knowing this will be important. This is a Lima-san with a dimple. Like I said, my stylus isn't working very well. I'm sorry. So negative cosine, most of the graph is going to be to the left. Add them up to get the long part of the Lima-san. 1, 2, 3, 4, 5. Subtract them. That tells you where the dimple's at on the other side. So 3 minus 2 is 1. And that first number of 3 is how far you kind of go up on the edges. 1, 2, 3. 1, 2, 3. And you try and create this little kind of dimple shape. It almost looks like a cardioid, but it doesn't go through the pole. Your parametric equations are 3 minus 2 cosine times cosine and 3 minus 2 cosine times sine. Okay, these two are both roses. Oh, sorry, I forgot to write over here that this also graphs from 0 to 2 pi. Okay, so these are both roses. The first one is a 3-petaled rose, and the second one is a 4-petaled rose. So if you remember, if it has an odd number in with the angle, it's an odd number, that number of petals, and if it's an even number, it's double it. The first number is the length of the petal. Sorry. Excuse me. Oh, I'm so sorry. The odd petaled roses actually graph on the window 0 to pi, and the even petaled roses graph on the window 0 to 2 pi. So this sine rose then will have a petals of length 4, and because it is 3 petals, you're going to have one petal down on the negative pi over 2, and the other 2 will be on the pi over 6 angles. Again, I'm not doing a great job with this very bad stylus. Cosine roses will always have a petal on the polar axis. And then because there are 4 petals, they're going to always be split evenly. So there'll be one on this axis here, here, and down here. And your parametrics, I feel like I don't even need to write this anymore, but I'm going to at least write this one. 4 sine 3 theta times cosine theta, and y equals 4 sine 3 theta sine theta. Okay, I'm not even going to bother with number 6 because I think you get it. Remember to stop the video if you need to write more stuff down. I'm sorry that you don't have the handout, but you can always print it at home. Okay, so now we're going to move on to a couple more examples here that are more in line with calculus. So notice it says find the slope of the tangent line here. So if we're talking about the slope of the tangent line, excuse me, you need to think about what that means. It means you need a slope, okay? But the tangent line would be in terms of x and y, but this is in terms of r and theta. So one quick thing I want to do is just sketch this rose here so that you can kind of get an idea of what the answer is going to be. And then once you get the answer, like maybe it'll help it make sense in the future. Okay, so if I were to draw this rose, it's a sine rose with 4 petals. So, each of the petals will be on the pi over 4 angles. Okay, so something like this. The tangent line that we're talking about, it says tangent at x equals theta equals pi over 4. So we're talking about this line. So I hope you can kind of take a guess at what the slope would be there. I'm not going to tell you, but I hope you can guess. To get to this answer, then you're going to have to find the slope, but in terms of x and y. So you're going to have to write your parametric equations first. So I've got y equals 2 sine 2 theta times sine theta. And then you've got x equals 2 sine 2 theta times cosine theta. So we need each of those derivatives, and then you're going to substitute pi over 4 into those derivatives to find the slope. So this is going to be a little bit of work because it's a chain rule and a product rule. So we're going to try our best to, I'm going to try my best, and not we, to make this legible for you. So I need dy d theta. Okay, so remember y was 2 sine 2 theta sine theta. So my chain and product rules would turn out to be 2 sine 2 theta cosine theta plus, and I'm simplifying all of this out. So if you are not sure where I got these answers from, please just pause and then try it on your own. So that way you believe what I'm getting here. But again, for the sake of trying to make the video not be too long, I'm just going to go through this a little bit faster than I normally would. Okay, so this is negative 2 sine 2 theta times sine theta minus, plus 4 cosine theta cosine 2 theta. Okay, and we're thinking of this as a slope, so we want to think of dy d theta over dx d theta. We're just thinking of this as, just like when we did the parametric equations, this is parametric equations, so we're thinking of dy d theta over dx d theta gives dy dx. It just happens to be in terms of theta, but this is dy dx. And now we're going to evaluate this at pi fourths. Okay, so let's see what we get here. We've got 2 times sine of pi halves, which is 1, times cosine of pi fourths, which is root 2 over 2, plus 4 times pi fourths, which is root 2 over 2, and cosine of pi halves, which is 0. But I wrote theta, which is 0. So that, I did it again. So that, I literally almost did it a third time, you guys. That's gone for that part. And then in my denominator, I get negative 2 sine of pi halves is 1. Sine of pi fourths is root 2 over 2. Cosine of pi fourths is again root 2 over 2 and again 0. So it looks like I get pretty much the same situation going on here. So again, this part is gone. So I'm just left with 2 over negative 2, which is negative 1, which would be the slope of that line, which again, if you thought about it from the very beginning, I hope you were able to believe that the slope of this line, which is perpendicular to the pi fourths line, is negative 1 because the pi fourths line is positive 1. Okay, moving on. So here's the next example here. This problem, I wrote all my notes down so I wouldn't have to scroll back and forth, but I'm trying to find it here. So this problem is asking you to find dy d theta and dx d theta, and it's actually I think an easier problem than the one we just did. So I feel like I don't need to spend a lot of time on that. I'm not so worried about this part, but I am going to find dx d theta and dy d theta. just finding the derivatives of dx d theta and dy d theta. I'm not going to worry about this part with the 3 pi over 4. So I'm going to write out x is equal to 2 sine theta cosine theta. And in order to make this a little bit easier to work with, I'm going to recognize this for what it is. And I hope you will too. 2 sine theta cosine theta is actually sine 2 theta, which will make it easier for me to deal with later on. Oops. So my derivative of x here would be 2 cosine 2 theta. Okay, and then my y is equal to 2 sine theta sine theta, which is 2 sine squared theta, which makes my derivative be 4 sine theta cosine theta. So that's a chain rule. But that could actually be rewritten as 2 sine 2 theta. So this is the same as 2 times 2, and then 2 sine cosine theta is sine of 2 theta. So I've just factored out a 2 there. So there's similar derivatives, I guess, is where I was trying to get to with that. Okay, I'm not going to worry about evaluating it. I think that you're probably fine with that. But I wanted to have it so that you could look at this problem now because it's using kind of some of the same information. So this is a weird problem. It's just kind of weird to think about here. And so I want to make sure we talk about this. So you're being told that you've got this same problem, r equals 2 sine theta, and you're told that d theta dt is equal to 5, which is weird because we don't have t yet in the problem. But that's what parametrics are usually talking about is time. But notice you want to find the values of dr dt at theta equals pi 6. There's a bunch of stuff going on here. So what you're going to need to recognize is you've got theta and t and r. And when you've got those 3 variables going on like that, it should, I hope, make you think of the chain rule here. Okay, at least I hope it will in the future. So if you are looking for dr dt, but you know you have d theta dt, if you could take d theta dt and multiply it by dr d theta, then you would have dr dt. So think about like what's being canceled here. So this is the chain rule. So the d theta dt times dr dt, the d thetas cancel, the d theta, cancel, and you're left with dr over dt. And there's some things you can fill in. So one of the things you can fill in is that d theta dt is automatically equal to 5. That was given to you. And you also were given that r is equal to 2 sine theta, which means dr d theta equals 2 cosine theta. So now you can fill 2 cosine theta in over here. So dr d theta is now equal to 10 cosine theta, and you were supposed to figure this out or evaluate this at theta equals pi over 6. So when you put pi over 6 in there, cosine of pi over 6 is root 3 over 2. 10 times root 3 over 2 would be 5 root 3. All right, last thing, we've got one additional formula you need to know. So this is the formula for arc length in polar form. Just like parametrically, it looks very similar to what we've seen so far. So it's just r squared, square root of r squared plus dr d theta squared in terms of d theta, and again from the bounds a to b. This one says to do this by hand, which I'm going to ask you to do it by hand on your own, but I'm not actually going to take the time to do it with you, just because I feel like this video is starting to run long. So the first thing I'm going to do is find dr d theta. So dr d theta is the derivative of 1 minus sine theta, which is negative cosine theta. And I'm going to evaluate this from 0 to 2 pi. Although that isn't the only way you have to do this, or you could do this. You could actually do this differently, which we can talk about that when I see you in person. But this then gets filled in as 1 minus sine theta squared plus negative cosine theta squared d theta. So I want you to see if you can figure out how to simplify this and solve it by hand. So see what you can do with that. All right. We will see you soon.